Welcome back everyone to our next video lesson in the series. We're going to be discussing electrical circuits, and we're going to start with a content called Ohm's Law. Okay, I'm using a FET simulation right now. This is the circuit construction kit, and I've already put into place some pieces of this electrical circuit. I'm going to show you right now what a simple circuit is. A simple circuit is the following. You see I have a picture of a battery, and I have some wires. These wires are connected all the way around to a light bulb, and you can see that there are moving electrons in this light bulb right here. See them? Moving around. So a simple circuit, like it sounds, the word circuit, like a word circle, means it goes around and around. You have three basic elements that are in a circuit. You have to have a power source. The source of power has a voltage or potential difference that provides the push of the electrons through the wire. Electrons don't really go through the wire, they actually go over the surface of the wire. We're going to get into that in a little more detail in another section. But for now, the electrons are pushed by the battery through the circuit. They come to the light bulb, they go in, they go around, and you see the illumination is taking place right here. And they come back to their source. So these are the basic three elements of a simple circuit. You have to have a power source, you have to have the conducting path, and you have to have the load on the circuit. That's where electrical work is done. Okay? So we're going to now take a look at something called Ohm's Law. The actual formula for Ohm's Law is given here on the reference table as the formula E5, which is something called resistance equals potential difference divided by current. It's not a very helpful form for you, so we're going to explain this in a lot more detail. Also, equation E4 is what is a current flow rate. It's the amount of charge that flows per unit time, and we will still be using potential difference, otherwise known as voltage, as work per unit charge. So in a moment I'm going to explain all three of these and how they fit into the circuit problem. Alright, now you see in front of you I have three magic triangles. The current flow triangle, the potential difference triangle, and the Ohm's Law triangle. And the most important thing to understand about these little magic triangles is that whatever are side by side are multiplied, and whatever is up and down are divided. So for example, current flow is defined as the amount of charge that flows per unit time. So I for current, the symbol for current is the letter I. It's equal to Q divided by T. That's called the charge flow rate. Coulombs per second, and that has a convenient unit called the amp or ampere, named after the scientist Ampere. So amps. Now we already have learned about potential difference, which is the work per unit charge. So there you have joules per coulomb, which turns out to be a volt. So voltage, even though it's not a real unit, it's a practical unit, is the work per unit charge. And then we have Ohm's law. So Ohm was a German physicist, and he discovered the push to flow ratio, that current can get through a wire based on two particular qualities of that wire or of that circuit. How much electrical push, which is going to turn out to be your voltage or potential difference, and how much a particular material in the wire, be it copper or tungsten or other materials, resist the flow. We're going to get a lot into this discussion right in a moment. So Ohm's Law, as you see here, we have a diagram, a formula, and an explanation, and a new Greek letter. So let's talk about that right now. As I said earlier, a simple circuit is a closed conductive loop where the charge flows through a load. It's a light bulb or other electrical device that you plug in. And it goes from higher potential difference to the low potential difference. Ohm's law mathematically is defined it defines resistance, which is the ratio of applied voltage to the resulting current. So really it's the push to flow ratio. So different materials are naturally resistant or conductive to greater or lesser degrees. So a resistor is a device that uses electrical energy, but each material has a resistance. So let's just take a look at this diagram. Here's your first circuit diagram. We're using symbols from the reference table. So let's take a look at what I have here. I have these long, short lines. This is the symbol for the battery or the source of the potential difference. These black lines represent the wires, and this squiggly with the letter R represents the resistor or the electrical element that is using electrical energy. Let's take a look at the reference table and see where these symbols are. So we're back at the reference table, and here you see circuit symbols. And this is right below the formulas on the electricity page. All right, we're going to get into all of those details above, but right now let's look at the symbols. We have an electrical cell. We have a plus and a negative. A long line is a plus, a short line is a negative. When we put a collection of voltaic cells together, we get something called a battery. This is the symbol for a switch. A lot of kids like to think of this as the drawbridge. When the drawbridge is opened, the electrons can't flow, just like a real bridge. When it's open, the cars can't pass over it. And we have some meters. We have a voltmeter. A voltmeter measures potential difference. It's got the letter V inside the circle. And we have an ammeter, and an ammeter is a letter A inside the circle, and that measures the flow of charge through that wire where that meter is going to be placed. We have the resistor. This is the squiggly symbol for the resistor, and that could be a light bulb. And we're going to show you a little later why they came up with the symbol for the resistor. It's really the diagram of a crimped piece of tungsten, which was the original material that glowed inside the first light bulbs. And then we have a variable resistor, and it has arrow, shows that it can slide back and forth. It's a symbol meaning that you can have more or less resistance. And then finally we have a lamp. And when they say lamp, they really mean the light bulb lamp. All right, let's continue. Okay, the last thing we're going to look at in this video is how a simple circuit is like an electric hill. So what we're going to do is take a look at the picture on the right, and we see here a triangular inclined plane, and there's a woman lifting, say, a ball, and she places something up on top of the shelf, right? But if this mass was permitted to roll down the hill like this, see, it would go from a high potential energy back down to a low potential energy. And then, of course, we'll have it roll back, and she picks it up, she puts it back up, but it continues to flow around. So as long as this woman here in the picture has the energy to continue lifting this ball, putting it up top, letting it roll down, picking it up again, and so on and so forth, she is creating what we would say is a mechanical circuit. So she is the source of the energy and the source of the flow. In the case of why the ball comes down, well, that's gravity doing the pulling. But the person is doing the work in moving the mass from low potential to high potential. Then the mass flows down the ramp from high potential to low potential, and it goes from a high PE to a low PE. And of course there could be, right here, could be some friction that produces a bit of heat, and there's a little bit of loss right there. Now let's take a look at the analogy. Let's look at the electrical analogy. So if you understand a woman picking up a ball, putting it up on top of the shelf, and it rolls down, it comes back, and she just keeps repeating this process, you should have no trouble understanding how a circuit works. So the battery is picking up the charge to the top of the high potential, and it rolls down, it flows down, and gets back here, this charge, it gets returned and it goes around and around. All right, so this battery picks up the charge to a high potential and allows it to then roll or flow down to a low potential, and it comes back around and the charges just keep circulating like this. Now right here in this spot, there's your squiggly line. That is actually the light bulb in symbolic form, but there is energy being used at this section right here. That's the light bulb. So the charge flows from high to low potential, but spends some of its energy in the form of heat and light, and maybe even sound. You may have heard light bulbs buzzing. They're hot, they glow, and there's like a bzzz coming out of them. That's energy being used. So this process repeats itself. So even though we draw the circuits in a square, let me show you the FET one more time. Okay, there's the FET one more time. You could see it's a square. However, just because the shape is a square, it doesn't mean that there isn't a high to low potential. All right, let's go back to the first diagram. And so in closing, if you understand this woman lifting up the ball and completing the circuit here, then you can understand that the battery is replacing the worker. So the battery is what does the work. It spends the energy, pushing the charges through the circuit. So these are analogous to each other. And this will conclude the introduction to Ohm's law and why a simple circuit even works in the first place. All right, we'll see you in the next video. Thank you for watching.